Swayam Prabha. Digital India. Educated India.
So here is the algorithm. So this is a very, very naive, simple algorithm which we'll call as the gradient descent algorithm. I'll explain why it's called the gradient descent in a minute. So you start from any position, any position, current position of your choice, and find the gradient at that point. So by gradient, in the previous case, it was just the negative. It was just the derivative. In higher dimensional, it is just the vector of partial derivatives in each direction, and then you make a jump from that point of a particular step size in the gradient direction, and then you keep and then you repeat. So that's all. It is the simplest. It's like one-line code in your Python or MATLAB, and it's the most effective algorithm to solve unconstrained optimization problem. Remember that we have not used any of the constraints. So the rope constraint or the fence constraint has not yet come into the picture. So this is an unconstrained version of the problem that we are looking at, right? So in this particular case, the negative gradient at 2, 2 is what? So you are trying to find the derivative with respect to so the x and y, the partial derivatives with respect to x and y. And if you look at the negative gradient at 2, 2, it is 4, 2, right? So I mean, this can be computed in this case. Which means what is 4, 2? 4, 2 is, this is 4 is in this direction, 2 is in this direction. So you are essentially, your negative gradient is pointing towards the grass, right? So the direction is 4, 2, which is pointing towards the minimum, right? So if you start at a different point, 1, 5, the negative gradient is 6 minus 4, which is 6 on the x-axis and minus 4 on the y-axis. You're still pointing to the grass. So the advantage of this is, if you travel in the direction of the gradient, the negative gradient always points to a direction of the minimum, direction in which the function reduces, and that's why this helps. So we'll see why that is indeed the case in a minute, right? So so to give some intuition as to, I mean, you started with the derivative, maybe it was just somebody said tangent, and when we tried derivative and it seemed to work, but then we want to kind of formally say why going in the direction of the derivative is the right thing to do, or is a good thing to do, or are there other directions? I mean, is the derivative the only direction in which you can travel? Are there other directions which also are good directions, right? Because the whole of optimization, at least in this basic version, is about finding good directions to travel. So how many of you remember this Taylor series? So what is what is your Taylor series doing? So you must have seen all this in your in school or maybe first year, right? So you basically, the Taylor series is just an expansion of a function. So you want to calculate the function at a point x plus epsilon d, right? So this is just a small number, let's say epsilon. And what is your Taylor series saying? It says that your x plus epsilon d can be evaluated in this particular form, which is okay, which is just a function of x plus epsilon d f prime of x, f double prime of x, double derivative, triple derivative, and so on. If the function is infinitely differentiable, this is an infinite series, and so on, right? So, but what is the beauty of this particular equation? It is the following. You can know information about this function at any point that you want if you know all the information about this function at the point that you are in, right? So basically, you are trying to evaluate this function at x plus epsilon d, which is somewhere else. But then if I give you all the information about f at x, meaning f of x, f prime of x, f double prime of x, and so on, that is good enough to understand everything about the function at any different point, right? So you can evaluate x plus epsilon d, which means you can evaluate it at any point if you have the derivatives of f at all the derivatives of f at x, which is interesting, right? So because the whole information about the function is captured in that particular value of that particular point and the derivatives at that point, which is interesting. And how can we use it, right? So if epsilon, which is equivalent to the step size that we are taking, right? So you are starting with x in our case, and then you want to evaluate the function at a different point. Let's say the next point that you are trying to evaluate is x plus epsilon d, where epsilon is your step size and d is the direction in which you are moving, right? So now, when epsilon is really, really small, right, so it's small enough, then all these terms, right, so because this is a function of epsilon squared, epsilon cube, and so on, if epsilon is like less than 1, then these numbers are like really, really small, so you can kind of ignore that in the approximation, and then look at only these 3 terms. Right? And for small enough epsilon, we have this equation. So from this equation, what can we say about the direction that we want to choose? You want to choose a direction d such that what happens to this term? So your goal, of course, was to minimize your objective f. You are trying to minimize f. You are at f of x. And in x plus epsilon d, how should f be with respect to x? Should it be more or should it be less? You are starting here. This is the current value, current objective value. This is the value of the new objective value. Your goal is to minimize f, right? So now, what can you say about this difference? What do you want this difference to be? So should it be high, low, positive, negative? It should be negative, somebody says. Why should it be negative? So forget the derivative. So we are not even talking about the derivative. We are just looking at this term, right? So if you want to move in the direction, in some good direction, so then this term should be negative, because only then you are minimizing the function. The objective is kind of reducing, right? So if f of x plus epsilon d was more than f of x, then you are not minimizing the function. So you're actually increasing the value of the objective, which is bad for you. You want to reduce the value of the objective, right? So which means this difference should be negative, correct? So now we know that for small enough step size by Taylor series, this difference is actually can be approximated like this, right? So now now this kind of gives us an intuition as to how to choose a d, right? So we want to choose a d such that this value is less than 0. Let's say our epsilon is always positive. We are always taking a positive step size, right? So the question now then becomes, what should be the value of d such that epsilon d f prime of x is as small as possible or is negative, correct? So now the direction, somebody said tangent, and then we tried out derivative, and then we said the negative of the derivative is always pointing in the direction that we want. So now if you plug in d as the negative of the derivative, what happens to epsilon d f prime of x? So you have epsilon d, 3 numbers. This is always positive, right? So you don't know anything about this. It could be positive or negative depending on x. Now, how can you choose d such that the whole thing is always negative? What is one way to choose d which will make sure that epsilon d f prime of x is negative? Sign of d, so which is what we exactly did, right? So if I set d as negative of f prime of x, then what happens to this? This just becomes minus epsilon f prime of x squared. We know this is positive, we know this is positive, and there's a negative. So there is a guaranteed decrease if you travel small enough in that direction, right? So which means, so the negative of in fact, it can be shown that the negative derivative is the direction in which you can do the descent is the maximum, right? So you cannot hope to descend more than this, right? So, but so is this clear at this point? So we made a choice of negative of derivative as the direction in which we need to travel, and Taylor series kind of tells us that this is indeed giving us a decrease in the objective function if you move small enough in the direction of the negative of the derivative. So any questions at this point till here? Okay. Something important to keep in mind, which we'll see as will become important in the next part of this talk, is it's not just the negative of the derivative, but it's any direction d such that d into f prime of x is less than 0 is a descent direction, right? So all we wanted was the product of these three terms to be negative. If that is guaranteed, then your function subjective value decreases. One choice was to take the negative of the derivative, and for which it is guaranteed to have a negative descent. But then that need not be the choice, always the choice, right? So any direction for which d into f prime of x is less than 0 is a descent direction. This is something to keep in mind because this will help us in the next part of this lecture. So this is all I had to say about unconstrained optimization. So any questions till now here? Okay. So to summarize for gradient descent, right? So it is the simplest unconstrained optimization procedure. It's extremely easy to implement because once you have the derivatives, you start at a point, move in the direction of derivative, repeat. If you choose a step size properly, then you are guaranteed to converge to the minimum. It will provably converge to a local minimum, right? So what's the difference between local minimum and a global minimum? Do you have any thoughts on that? So let's say I have a function like this, right? So is this a local minimum or a global minimum? This is a local minimum. What about this? That's also a local minimum, but this is a global minimum. So now how can we say something is a local minimum? So what is the definition of a local minimum? Sorry? The lowest point of the whole function is here. That's not a local minimum, right? So this is the lowest point of the whole function. So but what about this point? The lowest point in the neighborhood, which means if there is a sufficiently small neighborhood, right, where this is the point which is smallest, this is the value which is smallest, right? So irrespective of which direction you move in that small ball or small interval around this point, the value strictly increases, or at least increases. It does not decrease, right? So that is a local minimum. So now, what does this then mean, right? So if step size is chosen properly, gradient descent will probably converge to a local minimum. So why can't gradient descent converge to a global minimum? We said the descent, whatever, if you choose the direction the right way, your function value is going to decrease, right? So if you do it properly, why can't it converge to this point? Why would it not go up? So why can't, so she says, so once, let's say I start here, right? And then gradient descent, I keep moving this way, and I reach the local minimum. What she's saying is it will not again move up. And why is that? We have chosen what? We have chosen a direction such that the function value decreases. So what is special about local minimum? So why can't, so here is a point where the function value is still smaller, right? Why is not going to that direction? So what do you mean stuck? Exactly, right? So what are we actually doing that? So at this point, let's say we are at this point, and now we want to find the next iterate, right? So what is our algorithm? You find the negative of the derivative and move a small step in that direction. But what is the derivative at this point? The derivative is 0, which means you're taking 0, length step in whatever direction, right? So you're not taking a step at all. Because the derivative is 0, you are stuck here, right? So this is by virtue of our algorithm. Our algorithm was to move in the direction of the negative derivative, and because the derivative is 0, so you won't move anymore, right? So you're stuck there. So that is what we mean by stuck. So it cannot like really move once it reaches the local minimum, right? So now here is a simpler question. So how can we modify the gradient descent algorithm? If you had to find the maximum of a function instead of the minimum, what would you do? You just take the positive derivative, right? So and the same argument that I gave goes through. So the direction of the derivative would be the direction of which will point to the maximum of the function, right? So if you keep changing, then it will move to the maximum of the function. So, so this is not the only method for optimization. Somebody said Newton's method at some point. So there are multiple other methods that can be used to solve, to minimize a problem, and the only difference between these methods is how you pick a direction in which you move, right? For the Newton's method, for instance, you put a tangent and then see the point where it hits the x-axis, and then you move to that point and so on. And you can use the second derivative and so on, right? So, but we won't talk about that now. So, but you can think about other methods. How can you modify your basic method to see if there are other methods which can pick directions in a better way? So let's move on. So now we'll go to functions of many variables. So this is what is more interesting to us, because our features are always or our parameters space, the W's that we are trying to learn, are always high dimension. And it's never like a y equal to x squared plus 2 function that we'll hope to minimize, right? So the equivalent of Taylor series in higher dimension is as follows. So now all your x's are bold, which means they are vectors, and your epsilon is still a number, which is just a step size, the amount in which you are trying to move. Your d is now what is really a direction, right? So this is a vector. It has both a magnitude and a direction. So it is, you're moving in a particular direction. There are multiple directions in which you can move, whereas in the one-dimensional case, it was either left or right. Now you can move left or right in each coordinate, right? And your Taylor series still gives something like this, right? So where again, okay, so by dot product, I know you know what I mean by dot product. When I said d transpose del f of x is just the derivative, partial derivative of the function with respect to each of the coordinates, and d is the direction in which you are moving. And Taylor series says, so this is just a d transpose del of x, which is just a number, where transpose is your usual matrix or vector transpose. So what is important to remember in this function of many variables and in the constraint case which we will talk about is that the negative derivative, yes, is still a good direction to move, but then we saw that d into f prime of x was less than 0, always gave us a decrease. The equivalent statement in higher dimension is d transpose into del f of x is less than 0, right? So this term has to be negative, because for small enough epsilon, all these terms are really small. You can ignore them. So, and you want the new point minus f of x to be less than 0, which means you want this whole thing to be less than 0, which means because epsilon is positive, your d transpose del f of x is less than 0 is what you care about. So how do you visualize this? So let's say you have a vector, right? So you are at this particular point, and your gradient is pointing in this direction, right? So del f of x. So now we know d transpose del f of x is less than 0 is a descent direction. Now what are the directions in this picture which will give us descent? Where are those directions? What do you think are the directions in this picture which will, if I move from this point, so in this point the derivative is pointing in this direction. So what are the directions in which I can move so that the function will reduce? So we know that it is given by this equation, d transpose f of x, del f of x is less than 0. But then what is that? Where is that in this picture? So for example, we know that if you move in the direction of the negative derivative, it definitely reduces, right? So where is the negative derivative in this picture? Which is the direction of the negative derivative? So this is del f of x. So what is the negative derivative? Minus del f of x, which would be this, right? So this is, let's say, minus del f of x. So this is one direction in which I can move, in which the function will reduce. But then any direction that satisfies d transpose del f of x is less than 0 is a descent direction. So where are those other directions in this picture? Which are those directions? So what is the equation of this line? Yeah, so with respect to del f of x, so if this is 90 degrees, let's say, right? So what can you say about the equation of this line? So let's say this del f of x was 1, 1. So what is the equation of this line? You said something. So this is x plus y equals 0, right? So if I had to write it in dot product terms, right? So this is x, y transpose dot product 1, 1, right? Is 0, right? So so think of this as our gradient del f of x, and think of this as our direction, such that d transpose del f of x is now 0, right? So this is the set of all points such that the dot product with respect to this vector is 0, right? So which means this is just the set of all points for which d transpose del f of x is 0, right? So this is the line which is perpendicular to the vector that you care about. Is that clear? If your gradient was just 1, 1, then this is line is x plus y equals 0, right? So which is just the directions, so which means if I move in this direction, so if I move from here to here, the gradient, I mean the d transpose del f of x is 0, so which means I won't find any change in the function value at all in this direction, in these directions. So now I'm asking, I know that if I move in this direction, the function is going to change because this is a negative derivative direction. So now I'm asking, what are the other directions in which I can move such that the function will reduce? So for example, can I move in this direction? Will the function reduce or increase? In other words, let me ask it in a different way. So if I move to this point, so what can you say about x plus y in this point, in this direction? Is it less than 0 or greater than 0? It will be less than 0. So what about this point? Will it be less than 0 or greater than 0? So for this point, is x plus y less than 0 or greater than 0? Less than 0. So what about this point? So what about this line? So is there anything on this side of the line for which x plus y can be greater than 0? Can you convince yourself, is it possible, is it easy to see why I take any point to the left of this line, your x plus y has to be necessarily less than 0, right? Just because this line has x plus y equals 0, right? X equals minus y. So anything on this side is going to have x plus y is less than 0. Anything on this side is going to have x plus y is greater than 0, right? So which means any direction on this side is a descent direction, right? So any direction on this side is a direction in which I can move such that the function reduces. So if I start with this point again to say, so then the gradient is pointing in this direction. So this is the direction in which the function doesn't change. This is the direction in which I can move, function increases, and this is the direction in which it decreases, right? So this will be important because we'll see why that can help in constraint optimization problem. Okay, so let's look at the constraint optimization problem. Earlier we looked at the unconstrained version where you just wanted to minimize something and gradient doesn't work. Now we are going to look at the constraint optimization problem where you want to minimize a function such that there is a constraint, and for simplicity let's assume the constraint is g of x equals 0. So right, so this is some function. So this was the distance to the grass, and this is some other function which is just let's say the rope constraint or the fence constraint or something like that. In this case, it's those constraints had an inequality, but then let's start with a simpler case where you have a constraint where g of x equals 0, right? So now let's define two things. These two things will be critical. Given a point x, we are going to define two things. One is a descent direction, right? So if you are at a particular point and you are going to move to a different point in a particular direction, right? Any direction that leads us to a decrease in the function, we'll call it a descent direction. Because you are descending you are descending with respect to the objective in that direction, right? The objective reduces in that direction. So your f of x prime, right? So which is the new point that you will end up in, will have lesser value, objective value, than f of x that you started off with. Hence, it's a descent direction. The other thing that to keep in mind in constraint optimization problem, because there is a constraint, is any point, you are at a point x, but then any direction which will lead you to a different point where the constraint is still satisfied is a feasible direction, right? So it is feasible to move in that direction because you are still good with respect to the constraint. So what is the constraint here? The constraint is g of x is 0, which means any direction which will lead to a point x prime such that g of x prime is also 0 is a feasible direction. Well, in your original x may or may not be have g of x equals 0, but then once you move to this new point and you ended up with a point where g of x prime is also 0, then that's a feasible direction, right? So these are two different things. So is it clear? So what these two things are, right? So you also want to minimize the function, but then you also want to be in the feasible set, right? So the function, because if you remember the cow grass example, the exact point of the grass, you could move to the grass, right? So the exact point of the grass will always be a descent direction, but then it may not be feasible because of your rope constraint and your fence constraint, right? So you also want it to be feasible. So say somebody gives you a point x star and claims it is the solution to the problem, right? So now what properties should you satisfy for this point x star that somebody claims is an answer to this problem? So there are two important things. One, of course, it should be feasible, right? So in the sense that, so the x star should satisfy g of x star is 0, but more importantly, at this point, because it's not just feasibility that we care about, we also want optimality, right? So we want the function to be minimum at this point, or at least locally minimum at this point, right? So which means what I claim is there must not be a descent direction that is also feasible. What happens if this condition is not satisfied? There are better points, right? So how will you find that better point? Why is there a better point? If this condition is not satisfied, what does it mean? It means the negative of this statement, it just says that there is a descent direction which is also feasible. Which means what? So which means I can move in that direction so that my objective reduces and I'm still in the feasible set, right? So which means I'll end up with a point which has strictly lesser objective value and it is also satisfies the constraint. So this point cannot be the answer to my question. Is that clear? So the conditions to check. So these are necessary conditions. So somebody tells you that x star is the answer, then of course it has to be feasible. This point itself must be feasible. If it is not feasible, then you can straight away say that, hey, the constraint is not satisfied, this cannot be the solution. Let's say it satisfies the constraint, but that is still not enough because you should not have a direction to move where you can reduce the function and still be feasible. Right? So if there was a direction in which you can still satisfy the rope constraint, but then it has strictly lesser distance to the grass, then I would rather move to that point than being here, right? So this is a necessary condition for any optimal solution. Let's see how we can formalize this and how this helps us lead to an algorithm.